Hi, welcome back to my class in number theory. For today, we will take up the floor and ceiling of a real number. These concepts, the floor and ceiling of a real number, were introduced by Kenneth Iverson in the 1960s. Kenneth Iverson introduced the concepts of floor and ceiling of a real number in the 1960s. We start with the definition of floor and ceiling. We let x be any real number, that is, x is element of R, the set of real numbers. Then, this notation represents the floor of the real number x. The floor of the real number x is the greatest integer that is less than or equal to x. And this notation represents or denotes the ceiling of the real number x. The ceiling of the real number x is the least integer or the smallest integer that is greater than or equal to x. So this notation denotes the floor of the real number x. Again, this notation denotes the floor of the real number x, and the floor of the real number x is the greatest, the largest, the biggest integer that is less than or equal to the real number x. And this notation denotes the ceiling of the real number x, and the ceiling of the real number x is the least or the smallest integer that is greater than or equal to x. The floor of the real number x is also denoted by, this is the notation for the floor of the real number x, and the floor of the real number x is also denoted by this notation or this notation. And this notation represents the greatest integer function. Again, the floor of the real number x, denoted by this notation, is also denoted by this notation or by this notation. And this notation or this notation represents the greatest integer function. Thus, under the greatest integer function, the value of the real number x is the greatest integer that is less than equal to the real number x, because the greatest integer function is actually the floor of a real number x. And the floor of the real number x is defined as the greatest, the largest, the biggest integer that is less than or equal to x. We now take some examples of floors and ceilings of some real numbers. For our example, consider the following. Find the value of the following. Number 1, this is the floor of the real number 1.25. And the floor of the real number, as we stated earlier, is the greatest integer that is less than or equal to the real number. The integers that are less than or equal to 1.25 are 1. 0 is an integer less than 1.25. The integers that are less than or equal to 1.25 are 1. 1 is an integer, it is less than 1.25. 0 is an integer, it is less than 1.25. Negative 1 is an integer, it's a negative integer less than 1.25. Negative 2 is a negative integer less than the real number 1.25. And all the negative integers are less than the real number 1.25. And among these real numbers, among these integers that are less than or equal to the real number 1.25, the largest, the greatest, or the biggest is 1. Thus, the floor of the real number 1.25 is 1. 1 is the greatest or largest integer among the integers that are less than or equal to 1.25. Number 2, this is the ceiling of the real number 1.25. And as we defined earlier, the ceiling of a real number is the least or the smallest integer that is greater than or equal to 1.25. And the integers that are greater than or equal to 1.25 are 2. 2 is a positive integer and 2 is greater than 1.25. Another integer greater than 1.25 is 3, positive 3. All the positive integers that are equal or greater than 2 are greater than 1.25. 4 is a positive integer and it is greater than 1.25. But among these integers that are greater than 1.25, the least or the smallest is 2. Thus, the ceiling of 1.25 is 2. 2 is the smallest or the least among the integers that are greater than or equal to 1.25. Next, we find the floor of the irrational real number pi. Pi is approximately 3.14. And the floor of pi is defined as the greatest integer that is less than or equal to pi, or 3.14. And one of the integers that are less than pi or 3.14 is 3. Three is a positive integer that is less than pi. 2 and 1 are positive integers that are less than pi or 3.14. 0 is an integer that is less than pi or 3.14. Negative 1 and all the negative integers are less than pi or 3.14. But among these integers that are less than, there is no integer that is exactly equal to pi. All these integers are less than pi, but among these integers that are less than pi, the largest or the greatest is 3. Thus, the floor of the irrational number pi is 3. Next, number 4, we find the ceiling of pi. The ceiling of pi is defined as the least or the smallest integer that is greater than or equal to pi. And one such integer that is greater than pi or 3.14 is 4. All the positive integers that are greater than 4 and including 4 are greater than the irrational number pi. 5 is a positive integer greater than pi or 3.14. The same with 6, 7, 8, and all the positive integers are greater than, all the positive integers greater than 4 are greater than the real number 5. But among these integers that are greater than 5, the least or the smallest is 4. Thus, the ceiling of pi is 4. Next, number 5, we want to find the floor of negative square root of 2. Now, square root of 2 is approximately to 2 decimal places is 1.41. So we want to find the floor of the real number negative 1.41. And the floor of negative square root of 2 or the floor of negative 1.41 is the greatest integer that is less than or equal to negative square root of 2 or negative 1.41. And what are those integers that are less than or equal to negative square root of 2? Square root of 2 is negative square root of 2 is negative 1.41. So we start with negative 2. Negative 2 is an integer It's a negative integer that is less than negative square root of 2 or negative 1.41. Negative 3 is a negative integer that is less than negative square root of 2 or negative 1.41. All the real numbers, all the negative integers that are less than or equal to negative 2 are less than negative square root of 2 or negative 1.41. And among these integers that are less than negative square root of 2, the largest, the greatest is negative 2. Thus, the floor of negative square root of 2 is negative 2. Number 6, we want to find the ceiling of negative square root of 2. Now, the ceiling of negative square root of 2 or the ceiling of negative 1.41 is the smallest or the least integer that is greater than or equal to negative square root of 2. And what are those integers that are greater than or equal to negative square root of 2 or negative 1.41? We start from 0. Zero is an integer that is less than negative 1.41. Also, negative 1 is an integer that is greater than negative square root of 2. Again, the ceiling of negative square root of 2 is the smallest integer that is greater than or equal to negative square root of 2 or negative 1.41. And what are those integers that are greater than or equal to negative 1.41? We start with negative 1. Negative 1 is greater than negative 1.41. 0 is an integer greater than negative 1.41. 1 is a positive integer greater than negative 1.41. 2 is a positive integer that is greater than negative square root of 2 or negative 1.41. And all the positive integers down to positive infinity are integers greater than negative square root of 2 or negative 1.41. But among these integers that are greater than negative square root of 2 or negative 1.41, the greatest, the largest is negative 1. And that is the ceiling of the real number negative square root of 2. Number 7. 7 is a natural number or a whole number. It's a positive integer and we want to find the ceiling of the integer 7. Again, by definition, the ceiling of the real number 7 is the smallest integer that is greater than or equal to 7. And what are the integers that are greater than or equal to 7? So we start with 7. 7 is equal to 7. And another integer greater than or equal to 7 is 8. All the positive integers that are greater than or equal to 7 are greater than or equal to 7. And those integers are 7, 8, 9, 10, 11 down to positive infinity. But among these integers that are greater than or equal to 7, the least or the smallest is 7. Thus, the ceiling of 7 is itself. 7. Number 8, we find the floor of the negative integer negative 5. By definition, the floor of negative 5 is the greatest integer that is less than or equal to negative 5. And what are those integers that are less than or equal to negative 5? We start from negative 5. Negative 5 is exactly equal to negative 5. We want the integers that are less than or equal to negative 5. And negative 5 is equal to negative 5. Negative 6 is a negative integer that is less than negative 5. Negative 7, negative 8. All the integers from negative 5, all the negative integers from negative 5 down to negative infinity are less than or equal to negative 5. But among these integers that are less than or equal to negative 5, the largest or the greatest is negative 5. Thus, the floor of negative 5 is negative 5. Now we will take an example on how to sketch the graph of the greatest integer function. I said earlier that the floor of the greatest integer function, the floor of a real number x is also known as the greatest integer function. Now we will take an example on how to sketch the graph of the greatest integer function. For our examples of how to graph the greatest integer function, consider the following problem. Number 1, y is equal to the greatest integer function x. This is actually the floor of x for values of x between negative 4 and positive 4. And we sketch the graph of this greatest integer function y equals the floor of 2x minus 1, where x, the values of x are those that are greater than or equal to negative 1. And we sketch the graph in the Cartesian plane where we write x in the horizontal axis, y in the vertical axis, and the intersection is the point 0 or origin. And we start with the graph of the greatest integer function, the floor of x for x between negative 4 and 4. And in sketching the graph of the greatest integer function, we start from negative 4, going to positive 4. Now, if x is equal to negative 4, the greatest integer function of 4 again, we start from the left side. This is the left end point of this actually closed interval negative 4 and 4. The values of x are from negative 4 and 4, including negative 4 and 4. So we start with x equals negative 4. If x equals negative 4, y is equal to the floor of negative 4, or the greatest integer function of negative 4. And this floor of negative 4 is the greatest integer that is less than or equal to negative 4. And the greatest integer that is less than or equal to negative 4 is negative 4. Thus, when x equals negative 4, y equals negative 4. And we plot this point in the Cartesian plane. X is negative 4. Y is negative 4. Now we consider values of x between values of x that are greater than negative 4 but less than negative 3. That is, we are considering the open interval negative 4, negative 3. We are considering the values of x that are greater than negative 4 but less than negative 3. An example of value of x in this interval is negative 3.5. And if we have x between negative 4 and negative 3, the value of the greatest integer function y a particular value of x that is greater than negative 4 and less than negative 3 is negative 3.5. Negative 3.5 is halfway between negative 4 and negative 3. And the value of y defined by this greatest integer function is the floor of negative 3.5. The floor of negative 3.5 is the greatest integer that is less than or equal to negative 3.5. And that integer is negative 4. So when x is negative 3.5, the value of y is 4. And this is true, the value of y or the floor of x, if x is greater than negative 4 but less than negative 3, is negative 4. The value of y for these values of x greater than negative 4, less than negative 3, is 4. So from negative 4 up to negative 3, the value of y is negative 4. What about when x equals negative 3? If x equals negative 3, then the value of y is the floor of negative 3. And the floor of negative 3 is the greatest integer that is less than or equal to negative 3. And that integer is negative 3. So when x equals negative 3, the floor of negative 3 is not negative 4. And to indicate that, we write an open circle here. When x is negative 3, the value of y or the floor of negative 3 is negative 3. And we plot this point, x is negative 3 and y is negative 3. X is negative 3 and y is negative 3. Again, we started with x equals negative 4 and the value of y or the floor of negative 4 is negative 4. And the floor of all real numbers x greater than negative 4 but less than negative 3 is 4 up to negative 3.00001. But when x is negative 3, the value of y, which is equal to the floor of negative 3, is negative 3, as indicated by this dot or shaded circle. Now we consider the values of x that are greater than negative 3 but less than negative 2. We now consider values of x that are greater than negative 3 but less than negative 2. An example would be negative 2.5. Negative 2.5 is greater than negative 2 but less than negative 3. If x is negative 2.5, which is between negative 3 and negative 2, the value of y is defined as the greatest integer of x, or the floor of x, and the floor of negative 2.5 is the greatest, the largest integer that is less than equal to negative 2.5. And that integer is negative 3. All the integers from negative 3 down to negative infinity are less than equal to negative 2.5. But the greatest of these integers is negative 3. Thus, if you take any real number greater than negative 3 but less than negative 2, the floor or the value of y of that integer between negative 3 and negative 2 is negative 3. Negative 3.99, negative 3.75, negative 3.5, negative 2.5, up to negative 2.0001. The value of y is negative 3. But if x is negative 2, the value of y is the floor of negative 2. And the floor of negative 2 is the greatest, the largest integer that is less than or equal to negative 2. And that integer is negative 2. It's exactly equal to negative 2. The floor, the value of y if x is negative 2 is negative 2. When x is negative 2, the value of y is negative 2. So at x equals negative 2, the floor of negative 2 is not negative 3. And we indicate that by, again, an open circle. Now we consider the real numbers greater than negative 2 but less than negative 1. An example of that real number is negative 1.5. If x is negative 1.5, the value of y is the floor of negative 1.5. And the floor of negative 1.5 is the greatest integer that is less than or equal to negative 1.5. And that integer less than negative 1.5. The greatest or largest integer less than negative 1.5 is negative 2. If x is negative 2.9, the greatest integer, if x is negative 1.999, very, very close to negative 2. If x is, we take values of x greater than negative 2, less than negative 1.1, or values of x between negative 2 and negative 1. If we take an x very, very close to negative 2, say negative 1.999, the floor of negative 1.999 is 2. It is 2. It is the negative 2. The floor of negative 1.999 is negative 2. Negative 2 is the greatest integer that is less than negative 1.99. If we take an x real number very close to negative 1, say negative 1.001, again the value of y is the floor of negative 1.001, and the floor of negative 1.001 is the greatest, the largest integer that is less than negative 1.001, and that integer is negative 2. Hence, if you take value of x from negative 2 to a real number very close to negative 1, the value of y is negative 2. And we indicate that by a line in the graph. But when x equals negative 1, the value of y is the floor of negative 1, and the floor of negative 1 is the greatest integer. The greatest integer that is less than or equal to negative 1, and that integer is negative 1. Thus, when x is negative 1, the value of y is negative 1 and not negative 2. And we indicate that when x is negative 1, the value of y, which is the floor of negative 1, is not negative 2. We indicate that by open circle. And as we said, if x is negative 1, the value of y is equal to the floor of negative 1, which is negative 1. Now we take values of x between negative 1 and 0. The real numbers that are greater than negative 1 but less than 0. Say negative 1/2 or negative 0.5. If x is negative 0.5, the value of y is equal to the floor of negative 0.5. And the floor of negative 0.5 is the greatest integer that is less than or equal to negative 0.5. The integers that are less than negative 0.5 are negative 1, negative 2, negative 3, down to negative infinity, but the largest of these integers is negative 1. So if x is negative 0.5, the value of y equal to the floor of negative 0.5 is negative 2. If you take a real number very close to negative 1, greater than negative 1, say negative 0.99, the floor of negative 0.99 is the greatest integer. The largest integer that is less than negative 0.99, negative 0.99, and that integer is negative 1. Also, if you take a real number very close to 0, say 0.001, negative 0.001. If x is negative 0.001, then the value of y is equal to the floor of negative 0.001. And the floor of negative 0.001 is the largest integer that is less than negative 0.001. And that integer again is negative 1. Hence, for the values of x that are greater than negative 1 but less than 0, the value of y is always negative 1, except when x is 0, because when x is 0, the floor of 0 is 0. The floor of 0 is the largest integer that is less than or equal to 0. and that integer is 0. So for values of x greater than -1 but less than 0, the value of y is -1. But when x equals 0, the value of y is not -1 because the floor of 0 is not -1 but 0. When x is 0, the floor of 0 is itself, and we indicate that by a shaded circle or a point. So when x is 0, the value of y is the floor of 0, and the floor of 0 is 0. Now we take integers between 0 and 1. Say 1.5. If you have 1.5, if x is 1.5, then y is equal to the floor of 1.5. And the floor of 1.5 is the largest integer that is less than or equal to 1.5. The integers that are less than or equal to 1.5 are 0, -1, -2, -3, 4. And the largest, the greatest of these integers is 0. Again, if we take values of x between 0 and 1, a particular value of x is 1.5. If x is 1.5, the value of y is the floor of 1.5. And the floor of 1.5 is the greatest integer that is less than 1.5. The integers that are less than 1.5 are 0, -1, -2, -3, -4 down to -infinity, but the largest of these is 0. So for any value of x greater than 0 but less than 1, the value of y is 0. Except when x is 1. Because if x is 1, y is equal to the floor of 1, and the floor of 1 is the greatest integer that is less than equal to 1. And that integer is 1. 1 is equal to 1. So when x is 1, the value of y is 1. And we indicate that by shaded circle or a point. This is the origin. Now we consider values of x between 1 and 2, real numbers that are greater than 1 but less than 2. Say 1.5. If x is 1.5, then the value of y is the floor of 1.5. And the floor of 1.5 is the largest integer that is less than 1.5, and that integer is 1. If you take a real number very close to 1, say 1.001, the value of y if x is 1.001 is 1. The biggest integer less than 1.001 is 1. If you take a real number very close to 2, say 1.99, if x is 1.99, the value of y is the floor of 1.99, and the greatest integer less than 1.99 is 1. Hence, for real numbers between greater than 1 but less than 2, the value of y is 1. except when x is 2, because when x is 2, the value of y is the floor of 2. And the floor of 2 is the greatest integer less than or equal to 2. And that integer is 2. When x is 2, the value of y is 2. But if x is between 1 and 2, not including 2, the value of y is 1. And that is indicated by this line. Again, for real numbers between 1 and 2, the value of y is always 1. The greatest integer function of x, if x is between 1 and 2, is 1. But when x is 2, the value of y is not 1, indicated by this open circle. But when x is 2, the value of y equal to the floor of 2 is 2. And indicate that by a shaded circle or a point. Now we take real numbers between 2 and 3, real numbers that are greater than 2 but less than 3. Say 2.5. If x is 2.5, the value of y is the floor of 2.5, and the floor of 2.5 is the greatest integer that is less than 2.5, and that integer is 2. If x is 2.5, the value of y is 2. If you take a number very close to 3, say 2.99, if x is 2.99, the value of y is the greatest integer function of 2.99, or the floor of 2.99. And the floor of 2.99 is the greatest integer less than 2.99, and that integer, that greatest integer less than 2.99 is 2. Hence, for real numbers greater than 2 but less than 3, the value of y is always 2. Except when x is 3, because when x is 3, the floor of 3 is not 2 but 3. Again, for real numbers from 2 up to 3 but not including 3, the value of y is 2. The floor of a real number greater than or equal to 2 but less than 3 is 2. If you take any real number in this interval 2 to 3, the value of y is 2. The floor of the real number between 2 and 3, excluding 3, is 2. But when x is 3, the value of y is 3. If x is 3, the value of y is equal to the floor of 3, and the floor of 3 is the greatest integer less than equal to 3, and that integer is 3 itself. So when x is 3, the value of y is 3, and we indicate that with a shaded circle or a point. Now we consider real numbers. We are almost at the end, at the right end point of this closed interval. We consider real numbers between -3 and between positive 3 and positive 4. We consider those real numbers that are greater than 3 but less than 4. Example 3.5, if x is 3.5, the value of y is the floor of 3.5, and the floor of 3.5 is the greatest integer, the largest integer less than 3.5, and that biggest integer less than 3.5 is 3. If you take a number very, very close to 3, say 3.01, the value of y is the floor of 3.001, and the greatest integer, the largest integer less than 3.001 is 3. If you take a real number very, very close to 4, say 3.99, if x is 3.99, y is equal to the floor of 3.99, and the floor of 3.99 is the greatest, the largest integer less than 3.99, and that integer is 3. But if x is 4, y is the floor of 4, and the floor of 4 is the greatest integer less than equal to 4, and it is 4. So when x is for real numbers between 3 and 4, greater than 3 but less than 4, the value of y is always 3. But when x is 4, the value of y is 4 and not 3. And we indicate that by an open circle. For real numbers between 3 and 4, the value of y is always 3. The greatest integer that is less than or equal to a real number between 3 and 4 is 3. Say 3.5, the greatest integer less than 3.5 is 3. When x is 3.5, the value of y is 3. When x is 3.001, the value of y is 3. When x is 3.99, the value of y is 3. But when x is 4, the value of y is not 3. When x is 4, y is equal to the floor of 4, and the floor of 4 is 4. When x is 4, the value of y is 4, and we indicate that by a point or small shaded circle. And this completes the graph of the greatest integer function for values of x from -4 to +4, including -4 and +4. For your practice and assignment, please try the following exercises. Number 1, find the value of each of the following. Letter A, you have the ceiling of E. E is an irrational number and it's approximately 2.7 something. B, you have the floor of -E. C, the ceiling of -E. D, the floor of +E. And letter E, you want this is actually another notation for the floor of a real number, and here we have the irrational number pi over 2. Letter F, this is another notation, the same notation for the floor of 72. Or in letter E, you want the greatest integer that is less than equal to pi over 2. In letter F, you want the greatest integer less than equal to 72, and that's the floor of 72. In letter G, you want the floor of square root of 5. And H, you want the value of the ceiling of square root of 5 over 2. And for number 2, sketch the graph of this greatest integer function y is equal to the negative of the floor of the real number x, where the real number x is between the closed interval from 2 to 4. And that completes our lesson for today on floor and ceiling. But we will continue this lesson in the next lesson. And if you have question about the lesson today, you ask your question in the comments below. But don't forget to subscribe to my YouTube channel, Art Calison, the channel of learning and leisure. Or you may ask your friends, your classmates, your neighbors, and relatives to subscribe to my YouTube channel, Art Calison, so they may learn as well. Thank you for joining me in my class today in number tuning.